Okay, so logarithmic and exponential derivatives. This is a subset of the transcendental functions as well that we were just doing with the trigonometry. There's a little more detail involved in this. That's why I separated it into a separate section. But hopefully you've done the do now. If you need to review logarithms, it's something that you were supposed to do both from Algebra 2 and pre-calculus. I'm happy to help if anybody needs it, but there is also, I put in the content library in a logarithmic tab in there with extra practice problems. If you need more, just let me know. Question number 3 is a review from the limit section that we did. And question number 4, the denominator's base, it's both the numerator and the denominator has exponentials or exponential functions, but the base in the denominator is higher than the base in the numerator. You know that e is 2 point something where pi is 3 point something. So having a higher base will mean that that function will grow faster. So if the denominator grows faster, then we are going to approach 0. Okay, so looking at a couple, this here is supposed to be a review as well, that you can rewrite a to the x power as e to the natural log of a times x. And to explain why that happens, by the way, you could let a to the x equal y, and then take the natural log of both sides. So the natural log of a to the x is equal to the natural log of y, and then using the exponential rule here, you can move the x out in front. That's one of the properties of logarithms. And then, I'm going to rewrite this in exponential form from the perspective of the right-hand side. So I'm going to say, all right, that's going to be e to the power. I'm going to use this as the power. X times the natural log of a is equal to y then. But y was defined as a to the x. So then I get a to the x is equal to e to the natural log of a times x. Like that. And that's the proof for this, why that ends up happening. So my first step is then to rewrite some of these exponentials as a base of e instead of base of 3. Because when I can take the derivative of something that has base e instead, that means I could rewrite this fella here as e to the natural log of 3 times x. So right here, that's going to be its exponent. I know how to take the derivative of that. Now try and rewrite 5 to the x and 10 to the x plus 2. Same way. Pause it if you need to. Whoops. That's what I'm getting here. And I didn't mean to erase that. All right, same for logarithmic. It's called the change of base formula, actually, this here, if you remember this. But I can do a similar little proof for this. If I let y equal log base a of x, and then I can rewrite that in exponential form. So that gives me a to the y power is equal to x. I can take the natural log of both sides, so natural log of a to the y, natural log of x. Then bring the y out in front, so y is equal to the not equal to, y times the natural log of a is equal to the natural log of x. And then y is equal to the natural log of x over the natural log of a, but y is up here defined as log base a of x, so I'm just substituting that in there, is equal to the natural log of x over the natural log of a, which I could rewrite as 1 over the natural log of a times the natural log of x. And again, we know the derivative of the natural log of x, so that's why we're converting into the natural log of x. So using the change of base, then these two problems here, I could rewrite that as 1 over the natural log of this base here, 3 times the natural log of x. Or if you prefer to write it the natural log of x over the natural log of 3 also works. Now try the other two. So whichever way you prefer writing it. For calculus, it's useful to have it written as two separate things because 1 over the natural log of 3, for example, is just some constant value. Like you can take the number 1 and divide by the natural log of 3 on your calculator and you get some decimal. So there's no variable involved in there, it's just a constant.